on thermochemistry today. It will be a little bit different than some of what we've talked about this year, but you'll see where everything fits together as we go. Today we're going to talk about some basic terms. We'll be calculating heat transfer as well. Later on we'll get into calorimetry as well as interpreting and calculating change in enthalpy, change in entropy, as well as change in free energy. We'll talk about whether reactions are thermodynamically favorable. You'll see that's one of the criterion in order for a reaction to proceed. I'll also try and teach you some of the newer terminology. It may be slightly different than your textbook, but your book is a little bit older, and some of the newer terminology will be in the newer textbooks being released shortly. So first off, we just want to go over some basic terms. I've got a couple of YouTube videos for you to watch. A lot of what is in it is stated in your notes, so it's not like you'll have to take notes on it. It's just another take on it, but everything's listed here. You will see that thermodynamics is the study of all energy changes that accompany both physical and chemical processes. So you'll see, for example, even if you're just undergoing a change in state, if you're melting or freezing, there are still energy changes associated with those, and we'll talk about whether the reaction is endo or exothermic when it undergoes melting versus freezing. We'll also talk about energy changes that accompany chemical processes such as cellular respiration and photosynthesis that you learned about in biology last year. So we'll take a look at this first video here, and he's going to define some simple terms for you.
That was me last night.
Hey, what's up everybody? In this video we're going to talk about one of the most important and interesting, at least in my opinion, aspects of chemistry, and that is thermochemistry. So you can probably already make a pretty good attempt at guessing what thermochemistry is, owing to the fact that we have a picture of a power plant here on this slide. But let's actually go into the scientific definition of thermochemistry and see how far that takes us. So according to my chemistry textbook, the definition of thermochemistry is the study of the relationships between chemistry and energy. Okay, so now we're getting somewhere. So chemical reactions, some of them release energy, some of them require energy, some of them release a lot of energy, some of them release a little bit of energy. Some chemical reactions require a lot of energy to get going, some of them don't require much energy, and so on and so forth. So we're starting to get the idea of what thermochemistry is, but in order to understand this, we need to be able to define the word energy. Now, again, to define the word energy, I just kind of took another look in my chemistry textbook, and I found that energy is the capacity to do work. So it's kind of this cat and mouse game we're playing, where each new definition that we look at begs a question about the definition of another word. So with thermochemistry, now we have to define energy, and then with energy, the capacity to do work. Well, what the heck is work? So now we got to define work. And according to my chemistry text, once again, the definition of work is the result of a force acting through a distance. So again, energy. If something has energy, that means it has the capacity to exert a force on another object and move it through some distance. Okay, so now that we have just been inundated with vocabulary, it seems only fitting that we introduce a little bit more vocabulary, right? And so we're going to talk about some types of energy. The first type of energy that we're going to talk about is called potential energy. And the potential energy that an object has is associated with the object's position. Potential energy can also be associated with the composition of an object, so how that object is put together. And of course, we're going to elaborate on potential energy a little later in this playlist. So for instance, you see this little scientist over here who's holding up an apple relatively high off of the ground. That apple, simply because of its position within the Earth's gravitational field, has a lot of potential energy. And of course, if you release that apple, the apple would fall. And the reason why that's true is because scientists have determined that nature tends to proceed in a way that minimizes its potential energy. So whenever possible, nature is always going to try to do whatever it can to lower its potential energy and get it as low as possible. The second type of energy that we're going to discuss is called kinetic energy, and the kinetic energy of an object is associated with its motion. So something that is in motion has kinetic energy, something that is at rest has no kinetic energy. And finally, the third type of energy that we're going to talk about in this video, there are more types of energy, but for now we can just limit our discussion to 3. The third type is called thermal energy. So here's a nice photograph of the sun that I found. And as you've probably already figured out, thermal energy is associated with an object's temperature. And thermal energy is actually a type of kinetic energy because thermal energy originates from motion, just as regular old kinetic energy does. Thermal energy originates from the motion of particles. So you have atoms and molecules moving around. You may have some subatomic particles moving around really fast. All of those atomic, molecular, subatomic particle motions are what are the origin of thermal energy. So again, we have potential energy, that's due to position or composition. Kinetic energy, that's due to motion. And then we have thermal energy, which is associated with temperature. And remember, thermal energy is a type of kinetic energy. So the last thing we're going to do before we wrap this video up is talk about some of the most common units of energy. And there's a lot of units of energy out there, and we're going to talk about just a few here in this video. Now, the SI unit, remember SI stands for International System of Units. The international unit for energy is called the joule, and it has the symbol capital J. And the joule is a derived unit, so it comes from other SI units. And the definition of the joule is 1 kilogram times square meters divided by square seconds. Okay, now the joule is not a very large unit of energy. There's really not a lot of energy in a joule. And so oftentimes you're going to see energy reported in kilojoules, where of course 1 kilojoule is equal to 1,000 joules. Now another common unit of energy is the calorie, which I'm sure you are familiar with, and that has the symbol lowercase cal. And the definition of the calorie is the amount of energy that's required to raise the temperature of 1 gram of water by 1 degree Celsius. And if you wanted to convert between calories and joules, you could use this relationship over here, where we have 1 calorie is equal to 4.184 joules. So we can see in this relationship that the calorie is a larger unit of energy than the joule because there's more than 1 joule in 1 calorie. Closely related to the calorie is the nutritional calorie, and the only thing different about the nutritional calorie, at least if we're looking at the symbols, the only thing that differentiates the symbols of regular old calories and nutritional calories is that in the nutritional calorie, the C is capitalized, so it's capital C-A-L. And there are 1,000 little c calories in a big C nutritional calorie. And so when you look at the nutrition facts on the back of your milk or your donuts or whatever, what you're reading talks about all the different calories, calories from fat, total calories per serving, all that stuff. Those calories are the nutritional calories, the big C calories. So if you take those calories and multiply them by 1,000, that's how many little c calories you have.
So your 2,500 calorie diet that most of you are probably on, that's 2.5 times 10 to the third. Little c calories is really 2.5 times 10 to the 6. So, because your little c is actually a big C, and so if you make it a little c, let me write that out, that's going to be confusing. So if you're on a 2,500 calorie diet, that's 2.5 times 10 to the third calories. And keep in mind here that 1 nutritional calorie is 1,000 calories or 10 to the third calories. So if you went and converted this now to little c, that's actually 2.5 times 10 to the 6th little calories. And that would be a very, very large number, and that's one of the reasons the nutritional calorie is going to be a capital C. And we'll talk about these types of conversions when we do the lab, where 1 calorie is equal to 4.184 capital J for joules. And we'll talk about how to use those conversions. You already know how to do the factor label method, so you wouldn't have any difficulty making those types of conversions.
In one serving of whatever you happen to be eating. Now, the last unit of energy that we're going to talk about before we are all done here is...
And we're not going to deal with kilowatt hours. That would be a little bit different. You may be familiar with watts and kilowatts and light bulbs, things like that. So he covered some very simple terms that we'll get into in a minute. I also want to mention the first law of thermodynamics, and that says that energy is neither created nor destroyed in a chemical reaction. It's simply converted from one form of energy to another. For example, with cellular respiration, where you have glucose and oxygen gas yielding CO2 and water, you convert energy into more usable forms. So you've got energy in sugar, and then you convert it to more usable forms. With photosynthesis, you convert light energy from the sun to forms of energy that the plant can use. So these all involve conservation of energy, and we're just going to watch a short piece right here because he explains this concept well.
Hey, what's up everybody? In this video we're going to talk about the first law of thermodynamics.
Now I know Miss Stedman would be horrified by this statement. It's lacking a period, and he has a contraction that doesn't exist.
So to start off with this lesson on the first law of thermodynamics, I'd like to share a quote with you, and the quote reads, "There ain't no such thing as a free lunch," meaning you can't get something for nothing. Now this quote is usually used and it relates to things like business and economics and finance and that sort of thing. But as we'll see shortly, this quote could also be related to thermochemistry and the first law of thermodynamics. So what does the first law of thermodynamics say? Well, the first law simply says that the total energy of our universe is constant. It does not change, meaning that energy cannot be created and it also cannot be destroyed. So if you give energy to one thing, that energy has to come from somewhere else. It can't just come from nowhere. So it's the same sort of thing. You can't get something for nothing. No such thing as a free lunch. And to simplify our discussion on the universe, it's very useful to think of the universe as consisting of only two components that we call the system and the surroundings. So imagine this big green square, green and purple square, is the universe, and then there's two components. The outer square is the surroundings, and the inner square is the system. Now the system of the universe is defined as the part of the universe under study. So whatever you happen to be studying, whether it's a chemical reaction vessel, it could be the room, it could be your entire planet, it could be our solar system, it could even be the entire universe itself, just whatever you have defined the system to be. Now typically, when we start talking about chemical reactions and the energy changes associated with those chemical reactions, the system is going to be defined as the reactants and the products of the chemical reaction. So let's just keep that in mind. And then the surroundings is simply everything else in the universe that is not the system. So the first law of thermodynamics has to do with energy changes that take place between a system and its surroundings. Let's talk about sign convention for this moment. Sign convention refers to what you choose to be positive and what you choose to be negative. So energy could either be flowing from the system into the surroundings or from the surroundings into the system. If energy is flowing from the surroundings into the system, in other words, if the system is gaining energy while the surroundings lose energy, we consider this a positive change in energy. So the point of view is essentially on the system. If the system gains something, that's considered a positive change. Conversely, if you go in the other direction, so in other words, if energy is flowing out of the system into the surroundings, so the system is losing energy and the surroundings are gaining energy, well, this is considered a negative change. Okay, so this is the sign convention that has been adopted by scientists. I don't know if there are any scientists that do it the opposite way. Most of them do it this way, where if the system gains something, it's positive, and if the system loses something, that's considered negative.
And we'll talk more about that throughout the chapter. We probably won't get into it today, but we'll get back to it. What controls whether a reaction occurs are two factors. The first factor or question you want to ask yourself is the reaction thermodynamically favorable or spontaneous? Does it occur without any assistance? The older textbook used the term spontaneous. The newer books, AP, College Chem, they're tending to use the phrase thermodynamically favorable. Is product formation favored? Does the reaction occur without any assistance? And that's what we're going to look at in this chapter. In the subsequent chapter, we're going to look at whether the reaction is kinetically favorable. That is, does it occur fast enough? We're going to be looking at reaction rates. In order for a reaction to occur, both criteria must be met. The reaction must be both thermodynamically and kinetically favorable. If you look at the conversion of diamond to graphite, it turns out that graphite's actually more stable than diamond. So this reaction is thermodynamically favorable, but it occurs so slowly, it's not kinetically favorable, that the reaction doesn't proceed in the forward direction without outside intervention. In contrast, in a lab we ran earlier this year, we looked at silver nitrate and sodium chloride. We generated a white precipitate. So this would have been your solid silver chloride and sodium nitrate. And this reaction did occur without any assistance. It's both kinetically and thermodynamically favorable. So in order for a reaction to occur, it must be both thermodynamically and kinetically favorable. And years ago, this was a very simple question on the AP exam, and a lot of the kids missed it because they were confused in linking the two criteria together, which is why I mention it at the beginning of this chapter, and we'll mention it at the end of the second chapter that we cover, the one after this. Some very simple terms, and again, this is what the video really went into. Energy is the capacity to do work or transfer heat. Many, many different types of energy listed here. The unit for energy is the joule, capital J for joule, and this conversion, if you needed it, would be provided to you. You will need it on your lab where we're burning potato chips to figure out their caloric content. So this will be your chance to play with fire this year. We'll be trying to determine caloric content of potato chips, and very often the kids want to look at other foods as well. So we'll have that opportunity, just no nuts or peanuts in case we have any allergies. We don't want anybody to be sick. As he said, a calorie is the amount of energy needed to increase the temperature of 1 gram of water 1 degree Celsius, and nutritional energy has a unit of capital C calorie, which is really 1 kilocalorie, because 1 kilocalorie is 1,000 little calories, etc. Total energy is the sum of the energies, both kinetic and potential. Energy is the capacity to do work. The energy unit is joule. Heat is the quantity of thermal energy, and that's transferred from one object to another. You can measure it based on a change in temperature. It's also known as the total random kinetic energy of atoms. Heat always flows from the warmer object to the colder object. If you went skiing up north over break, it probably was very cold out. You would come in, your hands and feet would be very cold, even though you had mittens and warm socks on. You might then put your feet by the fireplace and the heat would be transferred from the warm fire to your cold toes. Or maybe you had a mug of hot chocolate and you put your hands around it and the heat would be transferred from the warm mug to your cold fingers. Likewise, if you cook dinner, let's say you have some sort of casserole and whatever you made it in, that Pyrex dish is very warm. You don't want to put it in the fridge right away because heat would be transferred from the hot casserole to whatever's around it. And especially if you put it by milk or yogurt, some dairy product that would spoil at the higher temperatures, you would find that heat transfer from the hot dish to the cooler things in the refrigerator. One other key concept, you'll see that total heat content remains constant, so any heat lost by one must be gained by the other, and we'll talk about that concept when we talk about calorimetry later in the week. You'll also see that heat energy is disorderly atomic motion, whereas other forms of energy are orderly. The measure of disorder in a system is known as entropy, abbreviated with an S, and we'll get back to entropy later in the chapter, but entropy is a measure of disorder in the system, and you'll see that reactions tend to favor disorder. Disorder helps lead to thermodynamic favorability, and you can think of disorder with many examples. I'm sure your room on Sunday was nice and neat after mommy or daddy yelled at you 15 times to clean up what I refer to my daughter's room as a pigsty. So, of course, she was away for the weekend, so I cleaned it and everything was where I thought it should go. Well, she got home, and by Monday, you would have thought that a tornado went right through it because all the nice stacks that I made and I put the clothes away were all over the floor with the drawers open. Just a complete and absolute disaster. I'll be sure not to teach her about entropy because I can only imagine what the response will be. Please don't try it on your mom or dad. I don't think they'll appreciate it. If you have a deck of playing cards and you take it out of the box when it's brand new, how would you describe the organization of the cards? Highly organized. The cards are chronologically arranged and by suit. Suit?
Yeah.
Suit. Sounds funny. Anyway, very organized. And then you shuffle the deck and it looks somewhat like your room, a complete mess. And for those of you who are very neat, I apologize and I'm very proud of you. If you've ever been up north, as autumn turns into winter, it's very, very pretty in the fall where all the leaves have changed colors on the trees. As it gets colder and colder and the amount of day length decreases, we find that the leaves fall off the tree and what looked very, very pretty now is a complete mess, and then you have to rake them up. But we'll talk more about entropy later in the chapter. Heat. Quantity of thermal energy that's transferred from one object to another due to a change in temperature. And these terms you will need to know. I've made a crossword puzzle for you in your classwork, and that will help you learn these very simple terms. Temperature is a measure of the average random kinetic energy, not the total, but the average random kinetic energy. You'll see as temperature increases, average kinetic energy increases as well. When you measure temperature, you do measure it. It says measured in Kelvin. When you do most calculations, you'll need it in Kelvin, although it's typically measured in degrees Celsius, so I'm not in love with this. Let's say measured in degrees Celsius. And typically converted to Kelvin for calculations. However, delta T, the change in temperature, can go either way. And let me explain what that means. Let me go back. I know some of you were scribbling and I didn't quite give you the chance. I apologize. Okay, what I mean by that is when you want to calculate the change in temperature, capital T for temperature, you can do so by subtracting the initial temperature from the final temperature. So let's say you're heating an iron nail and your initial temperature is 10 degrees Celsius and you get it up to a final temperature of 120 degrees Celsius. The change in temperature would be 120 degrees Celsius minus 10 degrees Celsius, and that's equal to 110 degrees Celsius. And the change in temperature can be done in degrees Celsius, because even if you did it in Kelvin, you'd get the same value. If you added 273 to this, you'd have 393 Kelvin minus 283 Kelvin, and you get 110 Kelvin. So these changes are the same. So when we're doing delta T, we're just going to leave it in degrees Celsius. However, when you do other calculations in this chapter, you will need Kelvin. And we're going to use information about the change in temperature, the mass, and the specific heat to calculate what's known as heat transfer. Heat transfer is represented with a Q, and the amount of heat transfer depends on the specific heat of the substance, abbreviated lowercase c. This is how much heat is absorbed to raise 1 gram of a substance 1 degree Celsius. The unit is a little funky. It's joules per gram degrees Celsius. And on table 3, on the back of your second semester periodic table, you will find these specific heats. The substances are listed in the first column. The specific heat, abbreviated with a lowercase c in joules per gram degrees Celsius, are listed in the second column. Air has a specific heat of 1 joule per gram degrees Celsius. Carbon, that is in the graphite state, diamond and graphite do differ. They're both comprised of carbon, but one has a tetrahedral arrangement, which is diamond, and one has a trigonal planar arrangement, which is graphite. Graphite has a specific heat of 0.711 joules per gram degrees Celsius. Copper has a specific heat of 0.387 joules per gram degrees Celsius. What's the specific heat of silver? 0.233 joules per gram degrees Celsius. So you'll see what the substance is to find its specific heat. You'll see later on you'll be calculating specific heat to figure out what the substance is so you can determine an unknown. Heat transfer also depends on mass measured in grams, and the change in temperature, again measured in degrees Celsius. You can do it in Kelvin, but it's just not necessary. It's much easier to leave it alone. Here's your first formula for this chapter. Q is equal to MC, delta T. Let's take a look at these examples here, and then we'll provide you with some time. It says how much energy, so we're looking for Q, is required to heat an iron nail. So we want to know energy, that's what we're looking for. We've got an iron nail, that is pertinent information. The mass is 7 grams, and we want to raise the temperature from 25 degrees Celsius to 750 degrees Celsius. So let's take a look at how to process this. It's really very, very simple. We're looking for Q. The mass is 7 grams. The specific heat for iron is 0.448 joules per gram degrees Celsius off table 3. The initial temperature is 25 degrees Celsius. It attains a final temperature of 750 degrees Celsius. My delta T would be T final minus T initial is 725 degrees Celsius. Q is equal to MC delta T. The mass is 7 grams. The specific heat is 0.448 joules over grams degrees Celsius. You've got 725 degrees Celsius. Watch that unit cancellation here. The grams cancel, the degrees Celsius cancel. You're left in a unit of joules. And let's watch our sig figs here. We were given 2 sig figs on the mass. And so we want our final answer to be in 2 sig figs as well. You'll also note that I am entering quantities for each variable. Some of you are putting numbers all over the page and you're having difficulty driving it home. You would be far more successful if you worked with quantities. You would find a mistake early on. Out of the calculator I get this. In 2 sig figs I would have that. If you prefer this, that is also 2 sig figs, and I guess you could even do kilojoules if you were so inclined. So any of these answers would earn you full credit. Easy peasy? All right, let's try number 2. Number 2 is a little more challenging, but if you use the same approach to set it up, I feel very confident you'll be successful with it. On number 2, you have 4,582 joules of energy given, added to an 103 gram piece of copper at 10 degrees Celsius, so that is my initial temperature, and I want to know the final temperature. That's what I'm looking for. If you're ever looking for the final or initial temperature, I would still solve it as if I was solving for delta T, and then I would do a secondary problem to solve for the initial or final. I think you'll be more successful than trying to do it algebraically. So in this second problem, what we've got the Q is 4,582 joules. The mass is 103 grams, and we've got copper. What is the specific heat of copper? 0.387 joules per gram degrees Celsius. My initial temperature is 10 degrees Celsius, and I want to know my final temperature. My formula is Q is equal to MC delta T. I'm going to solve for delta T, and I do that by dividing both sides by MC. So delta T is equal to Q, (103 grams), 0.387 joules per gram degrees Celsius. My joules cancel, my grams cancel. I'm left with degrees Celsius in the denominator of a denominator, which flips it to the numerator for reasons we have already discussed this year. And so my change in temperature is 115 degrees Celsius. Now my delta T is equal to my T final minus my T initial. I want to solve for T final, something subtracted from it, so I will add it to both sides. Be very careful in your solving. It's easy to make an error. So I've got 115 degrees Celsius plus my initial temperature. When you add or subtract, you go to the least number of decimal places, not based on Siggy Wiggies. Be careful. And that is 125 degrees Celsius. Now, if you were solving for the initial temperature, it's going to be a little bit different. So watch your algebra there. Questions on number 2. Let's pull the variables out for number 3, and I'd like you to give it a try. Number 3 says if 60.03 joules of energy are added to a 50-gram piece of lead, so we're going to need the specific heat of lead, until a final temperature of 100 degrees Celsius is attained, what is the initial temperature? So use that information, get the specific heat of lead, and try and solve this problem. Give it a shot. have an answer? All right. That's what I got. So on number 3, you got the specific heat of lead. You solve for delta T. Now be careful algebraically here. You're going to subtract your delta T from the TF to get the initial, and you get 90.6 degrees Celsius. And then the last thing I want to mention, I'll flash that back on the screen just to finish out this piece. We have been calculating heat transfer where Q is equal to mc delta T. Substances that have very large specific heats are going to be able to store a lot of energy. For example, water and granite, if you look at this table, water has a specific heat of 4.18 joules per grams degrees Celsius. Granite's about 0.803 joules per gram degrees Celsius. And as a result, they can store a lot of energy. And that's why, for example, you have solar heated homes and they're going to store energy from the sun, things like that. We had a solar blanket up north on our pool. We didn't want to use the heater because the pool wasn't used that often. But the solar blanket would absorb heat from the sun, and that would keep the pool, at least it wouldn't lose so much heat overnight during the summer, because you only had your pool open from about Memorial Day to Labor Day up north. Down here we have our pools open year-round. So I want to leave you with one thought. If you have Q is equal to mc delta T, we had a change in temperature. But when a substance undergoes a phase change, such as freezing, boiling, melting, etc., the temperature doesn't change. So delta T would be 0. Yet you still have heat transfer when you have a phase change. So we're going to look next time at how to calculate heat transfer when you have a phase change. You won't be able to use this formula, but rather a different one. And that is the very, very beginning of thermochemistry, and we'll continue with it next time.